If you recall, when the curvilinear motion of a particle is studied in an x, y, z rectangular coordinate system, its position is represented by position vector r, and its instantaneous velocity v is dr dt, and its instantaneous acceleration a is the second time derivative of position r. And in general, r, v, and a are all three-dimensional Cartesian vectors. And don't forget this important conclusion that the velocity of the particle at any point is always tangent to the path. Now, let's look at this 3D curved path. It can be divided into small segments of curves with equal lengths. And when the segments get small enough, each one of them approaches an arc, which is a segment of a circle. And we know that a circle always falls in a 2D plane. And for the next small segment of the path, it can also be approximated by another arc that belongs to another circle that falls into another 2D plane. And then for another segment of the path again, it can be approximated by an arc that belongs to a circle that falls in yet a different 2D plane. This plane is known as the osculating plane, which in this case refers to the plane that contains the small arced path. As you can see, this plane changes at a different location and different time. The reason to define it is because now the 3D motion can be considered as a sequence of 2D motions that are limited within each plane. And we know that a circle always has a center and a radius. For the arc of the circle, these are called the radius and center of curvature. For the particle traveling at this location, we can define a pair of axes from it. The first one is the t-axis being tangent to the arc, and the other one is the n-axis pointing towards the center of curvature. It is also normal to the arc. And with the definition of the t tangent axis and n normal axis, we can represent the motion vectors using the tangential and normal components instead of the x, y, and z rectangular components. So for a particle, in a short moment dt, it travels along this curved path from location P to P prime. The distance traveled is the length of the arc on this path, ds. And at any given time, we can always set up a pair of axes from the particle. Again, a t tangent axis that is tangent to the path and always points towards the direction of the motion. Its unit vector is ut. And another n normal axis that is normal to the path, always points towards the center of curvature. And for the normal axis, its unit vector is un. And if you recall, the velocity vector is always tangent to the path. Therefore, the velocity vector written in the nt components is simply v equals to vut, with the scalar v being the speed or the magnitude of the velocity, and it equals to ds over dt. And the unit vector ut naturally indicates that the velocity is always in the direction that's tangent to the path. Here I'm skipping the mathematical derivation, but we can derive that acceleration will always have two components, a t, the tangent component, and a n, the normal component. Therefore, the acceleration is written in normal and tangential components as a equals to at ut plus a n un. The tangential acceleration at simply equals to dv dt, and the normal acceleration an equals to v squared over rho, with rho being the radius of curvature at this location. And since at and an are perpendicular to each other, we can easily tell from the Pythagorean theorem that the magnitude of acceleration is the square root of at squared plus an squared. Here are some important notes when you use the normal and tangential components to describe curvilinear motion of a particle. First, unlike the rectangular coordinate system, which is generally fixed on Earth, the anti-coordinate system is fixed on the particle instead. Therefore, it moves with the particle and is different from time to time. Second, one of the biggest advantages of using the anti-components is that the velocity always only has one component along the tangential direction. Third, the two components of the acceleration have distinct meanings. At only describes the change in the magnitude of the velocity or the change in speed, and an only describes the change in the direction of the velocity. And because the tangential acceleration fully describes the change in the magnitude of the velocity, therefore, as an important conclusion, along the tangential direction, the three basic kinematic equations apply, just like rectilinear motion that we learned before. Therefore, similarly, these three equations for constant acceleration apply too, but again, only to tangential motion. The normal acceleration an is also known as the centripetal acceleration, since it always points towards the concave side of the path, seeking the center of curvature. And lastly, if the curved path can be modeled by a function y equals to fx, then the radius of curvature at any given point can be calculated by this formula. Let's look at this example. An object is traveling along this curved path, and the equation for the path is given. If at this point shown at x equals to 16 meters, that the speed of this object is 28.8 meters per second, and also this speed is increasing at 8 meters per second squared, we need to determine the direction of the velocity, and also we need to determine its acceleration at this point, both magnitude and direction. Since we know that at any given point the object will have a velocity that is tangent to its path, we can set up the t-axis, which is tangent to the path, pointing towards the direction of motion, and an normal axis that is perpendicular to the path and points towards the center of curvature. And the velocity simply points towards the same direction as the tangent axis, and it has the magnitude of 28.8 meters per second. To determine the direction of the velocity is to determine the direction of the t-axis, which is characterized by this angle theta that it makes with the horizon. And because for the path, its equation is known, y equals to 1/4 times x to the 3/2 power. Therefore, its slope at any given time is dy dx, which equals to 3/8 times x to the 1/2 power. At x equals to 16 meters, we can evaluate the slope, which equals to 1.5, and this equals to tangent theta. Therefore, from here, we can solve for theta to be arctangent 1.5, which is 56.3 degrees, and that's the direction for the velocity, which is also the direction for the tangent axis. The acceleration written in the normal tangential components is ATUT plus ANUN. AT is the magnitude of the tangential acceleration, and it describes the change in the magnitude of the velocity or the change in speed, and in this case it's given to be 8 meters per second squared. AN is the normal acceleration and is evaluated by v squared over rho, rho being the radius of curvature at this point. And since the equation of the path is given, therefore rho can be calculated using this formula. So since y equals to, again, 1/4 times x to the 3/2 power, therefore dy dx equals to 3/8 x to the 1/2 power, and the second derivative equals to 3/16 x to the negative 1/2 power. And we can evaluate these two both at x equals to 16 meters to be dy dx equals to 1.5, second derivative equals to 3/64, substitute both into the equation for the radius of curvature, we can calculate at this point the radius of curvature is 125 meters. Therefore, if we substitute in the radius of curvature, we can calculate the normal acceleration to be 6.64 meters per second squared. And these two are the two components for the acceleration vector. Therefore, the magnitude of the acceleration is at squared plus an squared square root, which is 10.4 meters per second. And it's represented here visually. And the direction of the acceleration is characterized by this angle made with the horizon, and it equals to 56.3 degrees, which is the angle of the tangential axis plus arctangent 6.64 over 8, and totally that is 96.0 degree. And these two are the answers we're looking for, the magnitude and the direction of the acceleration.